All right, so you've memorized the reactions for this chapter. You're going to apply them to molecules, and so that's where we are in this video. You look at the carbon chain that they give you, you notice the pi bond, and so you know you're going to be doing an addition reaction. Those pi electrons are like extra molecular glue that you can use to add things onto that carbon chain. So what are you going to add? Well, that's where you look at the other stuff in the recipe. And these ingredients you would recognize from your studying of that reaction list that was given out for this chapter. Now, looking at this, you see these two steps. The first step has osmium tetroxide. The second step has either sodium sulfite or sodium bisulfite. And seeing those two ingredients in those two steps, those two separate steps, you would say, oh, this is syn dihydroxylation. And there are actually two ways that you might recognize syn dihydroxylation, two recipes that both accomplish syn dihydroxylation. One of them is with osmium tetroxide and either sodium sulfite or sodium bisulfite. The other one that we'll also practice with is potassium permanganate. It's a beautiful deep purple color with sodium hydroxide, and then you put it in an ice bath. So 0 degrees Celsius is the temperature at which water freezes. So it really just means put it in an ice bath in the lab. So both of those will accomplish syn dihydroxylation. Let's start with osmium tetroxide, and then we'll work with the potassium permanganate afterwards. Once you know what reaction you have, you want to sort of clarify for yourself what you're adding, where you're adding it, and how you're adding it, what direction the two groups are going to be added in. So the name is kind of telling you all this information. A hydroxyl group is a group that has a hydrogen and an oxygen. So we're going to be adding two hydroxyl groups because it's di, so two OHs. Where are they going to add? Well, there's no rearrangement, so they're always going to add onto the two carbons that were in the double bond. And then how are they going to add? Well, they're going to add syn. So they'll both be on the same side. Either they'll both be coming out at us, or they'll both be going away from us. And the other thing is, if you have a chiral center, you'll end up getting a racemic mixture, like in all of these reactions in this chapter, because your starting material is flat. And so there's a 50-50 chance that the reaction can happen on one side or on the other. And so it'll happen on both. And that's why you'll get both enantiomers in an equal amount, which is called a racemic mixture. So, okay, now that we've identified these things, we can apply them to this specific molecule. And in this molecule, you identify those two carbons in the double bond. That's where you're going to, because there's no rearrangement, that's where you're going to add the OHs. So you put an OH on one, you put an OH on the other. And in the process of doing that, you use up those pi electrons, so that pi bond is not going to be there anymore. And we do have a chiral center here, which means we need to draw both enantiomers. The chiral center is this carbon that is below. It's chiral now. And because they're syn, we might as well draw the bonds to both of these. Technically, because the top OH, this carbon that this top OH is on, is not chiral, technically you don't have to draw the three-dimensional direction for the bond to that. But it's kind of a nice detail to add, because syn is a large part of why you would do, because you want syn addition, that's why you would do this reaction rather than anti-dihydroxylation. So it's nice to draw them both syn. So you get both of those products in your answer, and you get them in about a 50-50 mixture. So that would be the product for this reaction. So we can take that same sort of thought process, apply it to another molecule. You'd look at this, you'd say, okay, I have a double bond, so I'm doing addition. What am I adding? Well, I see one step with osmium tetroxide, a second separate step with either sodium sulfite or sodium bisulfite, only one of those needs to be written. You would see those ingredients and you'd say, oh, this is a syn dihydroxylation. So let's apply that thinking onto this molecule. You look at the 2 carbons in the double bond. Because there's no rearrangement, that's where things are going to be added. So we're going to add the OHs to those 2 carbons. And here, as you do that, you use up those pi electrons so that pi bond isn't there anymore. Now you have a ring, and anytime you have a ring, you always have to show whether the 2 groups are syn or anti. In this case, of course, they're syn. And so you're going to have both of those groups coming out, or both of those groups going away. Now, technically, you wouldn't draw the molecule where these go away because it's just this same molecule all over again. Imagine taking this molecule and flipping it over like a pancake in a pan. In that case, both of these groups would be going away. But actually, that would be the case, that would be the case if you did not have this methyl group here, because you'd have a meso compound. But because we do have the methyl group, I take that back. I apologize for that. It's not a meso compound, and you will get both enantiomers. So you draw another molecule where both of these are going away. And the last thing you'd have to adjust is you'd have to change the direction that the methyl group is going in. Because this carbon is tetrahedral, so they need 2 bonds in the plane, 1 coming out, 1 going away. And the only thing that's missing on this is the 1 going away, so that's how we'll do the methyl group. And then on the other one, the only type of bond that's missing is 1 coming out, so that's how we'll draw the methyl group there. And so that would be the product for this particular syn dihydroxylation, or the products. You would get both of them. Now, that's not the only way you can see a syn dihydroxylation. You can also recognize a syn dihydroxylation when you have potassium permanganate at the top, beautiful purple solid, in clear sodium hydroxide solution in an ice bath. So if you do all of those, you'll get syn dihydroxylation. So you would take your molecule and you'd look at the 2 carbons in the double bond. That's because there's no rearrangement. That's where you're adding your 2 OHs. As you add them, you use up those pi electrons, so that pi bond won't be there anymore. And because we have a chiral center here, we need to draw both enantiomers. Our chiral center is this carbon right here. So we'll draw both enantiomers. One where both of these OHs are coming out at us, because they are syn, and one where both of those OHs are going away from us, because they're syn. And so you get a 50-50 mixture of those 2 enantiomers in this reaction. Finally, let's do one last example with potassium permanganate. You would look at this, you'd say, okay, I have a pi bond, so I'm doing addition. I have potassium permanganate, sodium hydroxide, and an ice bath, so I'm doing syn dihydroxylation. So we can take this molecule, look at the 2 carbons in the double bond. That's where you're adding your OHs, because there's no rearrangement. And we just have to make sure we draw these as syn. And as you add those OHs, you use up those pi electrons, so the pi bond won't be there anymore. So as we add these as syn, they're either both going to be coming out at us or both going away from us. And because we do have a chiral center, we have to draw both enantiomers. This is the chiral center right here, and then this is actually another chiral center, so we have 2 of them. So we're going to draw both enantiomers, one where they're both coming out and out at us, and one where they're both going away from us. And the last thing you want to fix on this molecule is you want to make sure that that carbon here is tetrahedral, and so it's going to have 2 bonds in the plane, 1 coming out at you and 1 going away. And for the left molecule, the one that is, it needs a bond that's going away. For the right molecule, it needs a bond that's coming out at you. And so that's how we're going to draw that methyl group that was there in the original reactant. So that those would be your two products for this reaction. So hopefully that gives you just a really quick sketch for the type of thought process you want to go through as you're predicting the products of these one-step syntheses for syn dihydroxylation.